Look up at the night sky. Every star you see belongs to a galaxy. Billions of suns bound together in a vast rotating system. The Milky Way itself is a colossal disk spinning at hundreds of kilometers per second, carrying our sun, our planets, and everything we know along for the ride. But here is the puzzle. Why do galaxies spin at all? In space, nothing moves without a cause. A spacecraft coasts silently until an engine fires up. An asteroid drifts aimlessly unless a planet pulls on it. Motion in cosmos always has a story. So when we see galaxies, each one a pinwheel of stars twirling in the dark, it raises an unsettling question. What started this motion and why hasn't it stopped? On cosmic scales, galactic spin isn't a trivial detail. It defines their very shape. Without rotation, galaxies would just collapse into amorphous blobs of stars. Instead, spin stretches them into elegant spirals, rings, or distorted ellipses. That rotation governs how stars are born, how gas clouds evolve, and even how supermassive black holes grow at galactic centers. The mystery deepens when you realize that galaxies aren't just spinning. They are spinning too fast. By our best calculations, the gravity from all the visible stars and gas isn't enough to keep them bound together. They should fly apart like a carousel, flinging riders off. And yet they don't. So where does this spin come from? Why does it persist for billions of years? And what invisible hand is keeping galaxies from tearing themselves apart? Those questions have led astronomers from the physics of the early universe to the hunt for unseen matter, and perhaps to the edge of new physics itself. When we talk about galaxies, we are not talking about small collections of stars sprinkled across space. We are talking about cosmic islands, each one a city of billions, sometimes trillions of suns, gas clouds, dust, and mysterious dark matter, all bound together by gravity. They come in different shapes and sizes, but one feature is nearly universal. They rotate. Take the Milky Way. Our home galaxy is a giant disk, roughly 100,000 light years across, spinning like a record at breakneck speeds. If you could look down from above, you would see glowing pinwheel with long spiral arms sweeping outward, every star locked into a vast gravitational dance. Our own sun takes about 225 million years to make a single orbit around the galactic center. That means in the 4.5 billion years since it's formed, the sun has only completed about 20 laps. Talk about slow runners. Not all galaxies look like neat spirals. Elliptical galaxies are more like cosmic footballs, huge rounded swarms of stars that orbit in random directions. They don't have the arms of spirals, but they still have overall motion and structure. Irregular galaxies, on the other hand, are cosmic oddballs. Distorted by past collisions or gravitational tugs, they look chaotic. Yet even they carry the imprint of spin in the way their stars move. Rotation isn't just a curiosity. It's the reason galaxies hold their shapes. If they didn't spin, matter would collapse straight inward under gravity, piling into a central lump. Instead, angular momentum spreads material out, flattening spirals into disks and stabilizing the vast systems we see across the universe. What's fascinating is that the scale of this spin is hard to grasp. Imagine every star in the Milky Way, about 100 billions of them, all orbiting in synchrony, like dancers in a routine. It's beautiful, but it also begs the question. How did galaxies acquire this spin in the first place? To answer that, we have to go back, way back, to the earliest days of the universe. To understand why galaxies spin today, we have to roll the cosmic clock back to when the universe itself was just getting started. In the beginning, right after the Big Bang, the cosmos wasn't filled with stars, planets, or galaxies. It was a hot, dense soup of particles expanding and cooling. But within this seemingly uniform sea, there were tiny imperfections. Regions where matter was slightly denser than the rest. Those faint ripples seeded in the early universe would eventually grow into galaxies. Now, here is where the physics kicks in. Imagine one of those gas clouds beginning to collapse under its own gravity. If it had even the tiniest bit of rotation, and almost all things in the universe do, that spin would intensify as the cloud shrank. It's the same principle you see when a figure skater pulls in her arms, conservation of angular momentum. The tighter the collapse, the faster the spin. Over millions of years, these collapsing clouds didn't just form galaxies, they created rotating disks of stars and gas. And once a galaxy had the angular momentum, it kept it. There is no friction in space to slow things down, unless another galaxy comes along to interfere. The spin established billions of years ago still shapes the galaxies we see today. Of course, gravity wasn't working alone. The large-scale structure of the universe, cosmic filaments and voids, also influence galactic rotation. Galaxies formed along these filaments of dark matter and gas, and the flows of material streaming in helped twist young galaxies into motion. So the answer to why do galaxies spin starts here. They inherited it. Their spin is a relic of the universe's birth, a memory of those first collapsing clouds. But here is the catch. When astronomers tried to calculate how fast galaxies should spin based on only their visible matter, the numbers didn't add up. Something else, something invisible was boosting their rotation and holding them together. And that's where the story shifts from the early universe to one of the biggest mysteries in modern science: dark matter. If galaxies are giant spinning pinwheels of stars, then here is the uncomfortable truth. By normal calculations, they shouldn't exist. When astronomers in the mid-20th century began measuring how fast stars orbit around galactic centers, the results didn't make sense. According to Newton and Einstein, the further out you are from the center of the galaxy, the slower you should orbit. It's like our solar system. Mercury zips around the Sun in just 88 days, while distant Neptune takes 165 years. Gravity weakens with distance, so outer stars should crawl compared to inner ones. But when astronomers actually looked, galaxies didn't behave that way. Stars far from the center were moving just as fast, sometimes even faster than stars closer in. The outer regions of galaxies were whipping around at impossible speeds. If only the visible matter were there, galaxies should have flown apart long time ago. Enter dark matter. To explain the strange rotation, scientists propose that galaxies are embedded in vast, invisible halos of matter we can't see directly. This matter doesn't shine, doesn't absorb light, and doesn't interact with normal atoms in any way we can detect, except through gravity. And yet, by weight, it completely dominates. Think of a galaxy as an iceberg. The stars, gas and dust we see are just the tip. The real bulk, the dark matter, lurks unseen, forming a massive gravitational framework that holds everything together. It's this hidden mass that explains why galaxies spin so fast without tearing themselves apart. The discovery was revolutionary. What began as a quirk of galactic spin became one of the biggest mysteries in physics. More than 80% of the matter in the universe might be this invisible stuff. Without it, galaxies as we know them couldn't even exist. So while we can't see dark matter, its fingerprints are everywhere. Each time a galaxy spins without flying apart, it's a silent reminder that most of the universe is missing from view. In the 1970s, a quiet revolution in astronomy began, and it started with a scientist named Vera Rubin. She wasn't looking to rewrite physics, she was simply studying how galaxies rotate. But what she found would change cosmology forever. Rubin and her colleague Ken Ford measured the speeds of stars and galaxies with extraordinary precision. They expected to see what Newton's laws predicted: stars near the center moving fast and stars on the outskirts moving slower, like planets in the solar system. The further from the mass, the weaker the pull of gravity, the slower the orbit. That's basic physics. But the data told a different story. When Vera plotted the rotation curves of galaxies, graphs showing star speed against distance from the center, the lines didn't drop off as expected. Instead, they stayed flat. Stars at the edge of galaxies were moving just as quickly as those near the middle. This became known as the galaxy rotation problem. By every visible measure, galaxies didn't have enough mass to hold themselves together. They should be flinging stars into intergalactic space like sparks from the campfire. But they weren't. Something unseen was providing the extra gravity. Rubin's observations gave overwhelming evidence for what we now call dark matter. She didn't discover dark matter, the idea had been floated decades earlier, but she provided the first solid, repeatable proof that it was real. Her work was initially met with skepticism. Some scientists wondered if Newton's and Einstein's equations simply broke down on galactic scales. Others thought Rubin's measurements were flawed. But study after study confirmed her results. Rotation curves across hundreds of galaxies showed the same flat pattern. What Rubin uncovered wasn't just an astronomical puzzle, it was a cosmic bombshell. If galaxies were mostly made of unseen matter, then the universe itself was built on a foundation we don't understand. Today we know that without dark matter, galaxies wouldn't form, wouldn't spin, and wouldn't survive. But even now, decades after Rubin's breakthrough, the true nature of dark matter remains one of science's greatest mysteries. Galaxies may look like serene whirlpools of stars, but the truth is they live in a universe that's anything but peaceful. Gravity is constantly pulling them together, and when galaxies get too close, things get messy. Their spins don't just evolve in isolation, they are shaped, twisted, and sometimes completely rewritten by cosmic encounters. Let's look at Milky Way again. It's not a lone wanderer drifting quietly through space. Even now, it's pulling in smaller dwarf galaxies, shredding them apart and weaving their stars into our spiral arms. And looming ahead about 4 billion years from now is the Andromeda Galaxy. On a collision course with us, Andromeda is speeding towards the Milky Way at nearly 400,000 kilometers per hour. When the two finally collide, their delicate spiral shapes will be destroyed. A new massive elliptical galaxy will emerge. That future collision will also reset the spin of both galaxies, changing the very identity of our cosmic home. Collisions aren't rare. In fact, the universe is full of galaxies in the middle of mergers, their shapes warped into bizarre bridges, tails, and rings. These gravitational tussles can either speed up or slow down rotation, depending on how the galaxies meet. Even near misses matter. When galaxies pass close by without colliding, tidal forces can twist their disks, stir up new star formation, and distort rotational patterns. Cosmic spin isn't just about what galaxies inherited at birth. It's also about who they've bumped into since. Every merger leaves scars. Every tidal tug reshapes the dance. Over billions of years, these interactions layer onto one another, making galactic rotation not just a relic of the early universe, but a living history written in starlight. So when we look at the Milky Way spinning steadily in the night sky, we are not just seeing ancient physics at work. We are seeing a snapshot of a dance that's constantly changing, one step in a story still unfolding. When you think of galaxies spinning, it's natural to imagine some grand order, as if the universe were a giant cosmic clock, with every galaxy turning in sync. But is that true? Do galaxies across the cosmos all spin in the same direction, like dancers following a lead? At first, the answer seemed to be no. Galaxies appear to spin in random orientations. Some rotate clockwise, others counterclockwise, depending on where you stand and how you look at them. From our point on Earth, roughly half of the galaxies seem to turn one way and half the other. On the surface, it looks like cosmic chaos, a universe with no preferred direction. But things get stranger the deeper we look. Astronomers analyzing surveys of thousands of galaxies have found subtle asymmetries. In certain regions of the sky, there appears to be a small bias. More galaxies spin one way than the other. These aren't huge differences, but enough to spark debate. Could the entire universe itself have kind of a built-in twist? If true, it would challenge one of the core assumptions of cosmology, that the universe is isotropic, meaning it looks the same in every direction. A preferred spin direction could mean the cosmos has a hidden structure or memory from its birth, something imprinted in the very fabric of space-time. Of course, not everyone agrees. Some researchers argue these patterns could just be statistical flukes, artifacts of the way we observe galaxies. After all, it's easy for human perception and telescope limitations to introduce biases. Still, the idea is tantalizing. If galaxies across vast distances share a faint alignment in their spin, it might point to forces at work in the early universe that we don't yet understand. Maybe cosmic filaments, those vast, invisible threads of dark matter, shepherd galaxies into a subtle order. Or maybe there is a deeper, unknown symmetry shaping the universe. For now, the question remains open. But whether galaxies spin clockwise, counterclockwise, or somewhere in between, their rotations remind us that even chaos has patterns waiting to be uncovered. It's very tempting to think of galactic spin as just an odd curiosity, like noticing in which way a ceiling fan is rotating. But in reality, spin is central to a galaxy's identity. Without it, galaxies wouldn't look the way they do, stars wouldn't form the way they do, and the universe itself would be a very different place. Take spiral galaxies like our Milky Way. Their graceful arms are sculpted by rotation. Gas clouds orbiting through the galaxy's disk getting compressed and stretched by the spiral structure. This compression triggers star formation, lighting up the arms with clusters of newborn stars. Without spin, there would be no spirals, just a shapeless blob of stars with far less starbirth activity. Spin also plays a huge role in the feeding habits of supermassive black holes. At the center of nearly every galaxy lies one of these monsters, millions to billions of times more massive than the Sun. As matter falls towards the black hole, the galaxy's overall rotation helps funnel gas into swirling accretion disks. The result? outbursts of energy, quasars, and sometimes powerful jets that blast material far into intergalactic space. Rotation influences structure on a larger scales too. The halo of dark matter surrounding each galaxy doesn't just provide gravity, it shapes how spin develops, stabilizing the disk and protecting it from tearing apart. Without dark matter's invisible support, galactic spin as we see it wouldn't even be possible. Even galaxy collisions, those cosmic smash-ups we talked about earlier, are shaped by the spin. The angle and direction of two galaxies' rotations decide whether the merger creates smooth elliptical, a ring, or a chaotic mess. Spin is the scriptwriter behind every galactic drama. And here is another kicker. Studying galactic spin gives us clues about the universe's past and future. The way galaxies rotate tell us about the forces that shape them, the role of dark matter, and even whether there are hidden patterns in the cosmos itself. So when we ask why do galaxies spin, we are not just indulging curiosity, we are asking why galaxies look the way they do, why stars form the way they do, and ultimately, why the universe has the structure it does. Every time we look at the Milky Way stretching across the sky, we are seeing more than just stars. We are seeing motion, a vast disk of hundreds of billions of suns all orbiting in a gravitational ballet that began billions of years ago. And the deeper we dig into that motion, the more it reveals. Galaxies spin because of ancient physics, seeded in the earliest moments of the universe. Their rotation is a memory of collapsing gas clouds magnified by angular momentum and sculpted by the invisible scaffolding of dark matter. Over time, collisions and encounters reshape that motion, sometimes amplifying it, sometimes erasing it, but never stopping it. That endless spin is more than a quirk of cosmic mechanics. It's the reason galaxies form spirals, why stars are born, why black holes feed, and why the night sky looks the way it does. Without it, galaxies would collapse into chaos and the universe would lack the structures that make it recognizable. And yet, for all we've uncovered, mysteries remain. Do galaxies across the universe share a hidden alignment? Does their spin hint at a deeper structure woven into spacetime itself? Or are we just watching the chaotic dance of countless systems, each with its own story? In the end, galactic spin reminds us of something profound. The universe is never still. From the smallest atoms to the largest clusters of galaxies, everything is in motion. And as our galaxy carries us on its endless journey around the cosmos, it leaves us with one undeniable truth. We are passengers on a ride that never stops. Thank you for watching. Keep looking up.